What was there before the Big Bang? Scientists have been trying to answer this question for years, but new finds are giving them surprising new information. Brian Cox and other experts have shown that the answer may be a lot trickier and scarier than we thought. Cox says the idea is that the universe wasn't hot and dense before the Big Bang, as we always think it was. It was cold, empty, and growing very quickly instead. The growth we're seeing now is called inflation, and it made the universe what it is today. But inflation didn't happen everywhere. It stopped in some places, which is what we now call the Big Bang, but it kept going in other places. This idea, called the inflationary multiverse, says that our world is only one of many. This point of view says that the universe is like a fractal with an endless number of Big Bangs happening in different parts of space and time. Every one of these areas turns into its own world, and ours is just a small part of a much bigger cosmic landscape. But what is inflation, and why did science find it so strange? Before the Big Bang, space grew very quickly, which is called inflation. It was caused by a strange kind of energy. At this point in time, space spread very quickly, making the universe look flat, and even by smoothing out any bumps. Then, the energy that was making the space expand was let go. This heated up space and made the particles that make up everything around us. We used to think that the Big Bang, this sudden burst of energy, was the start of everything. It was just a part of the universe's history, which brings up new questions. What did we have before inflation? Also, why does the world keep getting bigger? The universe is never really empty. The thought of absolute nothingness doesn't really work in space because it is so big. The universe wouldn't be truly empty even if we took away all of its energy. New types of energy are always being made as the world expands. Even when particles, photons, and radiation are not present, there are quantum fields, which are the building blocks of reality. Even in a void, this is the reason why space will never be completely empty, and the universe will always be making radiation. Even where there is nothing else, there can't be true nothingness, because these quantum fields make sure that something always stays the same. So, is it possible that there was nothing before the universe? According to what we know now, space still holds some energy even when it is completely empty. This zero-point energy is the most nothing-like thing we can think of, but it still stands for something, the lowest amount of energy that exists everywhere. The universe is growing from the past to the present. The world is always changing. As space grows, it pulls galaxies farther apart and cools the universe as a whole. In the beginning, after the Big Bang, the universe was hot and dense. But as time went on, it got bigger, colder, and less dense. As space grows, so does the light from faraway galaxies. This is why we see redshift, which is when the light waves from galaxies seem to get longer as they move away from us. This stretching causes energies to drop and temperatures to drop. This is why the universe is much colder now than it was at the start. It's possible to get rid of all matter and energy in the world, but what would be left behind? The answer is fascinating and deeply connected to the fundamental nature of our universe. Even if all matter and energy were removed, there would still be empty space. However, this empty space is far from nothingness. It is governed by the immutable rules of physics and filled with quantum fields. These quantum fields are the building blocks of reality, existing even in the absence of particles or radiation. Additionally, there is dark energy, a mysterious force driving the accelerated expansion of the universe. This dark energy ensures that space itself continues to grow, regardless of whether it contains any matter or radiation. Thus, the concept of complete emptiness is an illusion, as quantum fields and dark energy guarantee that the universe is never truly void. Inflation, the period of rapid expansion that occurred before the Big Bang, played a crucial role in shaping the universe as we know it. Before inflation, the universe likely contained a potent form of energy that caused space to stretch at an extraordinary rate. This rapid expansion smoothed out any irregularities or bumps, creating a universe that appears remarkably uniform and even. However, inflation also introduces new questions that challenge our understanding of the cosmos. For instance, where did inflation originate? If inflation occurred endlessly in some regions of space, producing countless Big Bangs, what does that mean for how we conceptualize the Big Bang? These questions push the boundaries of human knowledge and force us to reconsider the nature of existence. To explore these profound mysteries, scientists examine three interconnected yet distinct ideas: the hot Big Bang, the theory of cosmic inflation, and the concept of an ultimate beginning. Each offers a piece of the puzzle, yet none provide a complete answer on their own. The Big Bang and inflation are particularly linked in ways that continue to reshape our understanding of the cosmos. In the early 20th century, astronomers like Edwin Hubble and Vesto Slipher observed that galaxies were moving away from us. This discovery led to the groundbreaking realization that the universe is expanding. If the universe is expanding now, it must have been smaller and denser in the past, culminating in the idea of the Big Bang. According to this theory, all matter and radiation were once compressed into an infinitely small and dense point with an unimaginably high temperature. However, while the Big Bang theory explains much about the observable universe, it falls short in some areas. For example, it cannot account for why the universe appears flat or why it has such a uniform temperature across vast distances. These observations brought scientists to the theory of inflation, which offers compelling solutions to these problems. Inflation suggests that the universe underwent a brief but incredibly rapid expansion, smoothing out any initial irregularities and creating the flat, homogeneous cosmos we observe today. This rapid expansion also provides insights into why certain expected phenomena, such as magnetic monopoles, are absent in the universe. Despite its explanatory power, inflation complicates the Big Bang theory by implying that the Big Bang may not have been the true beginning of everything. Instead, it might represent a transition from an inflationary state to the hot, dense universe we now observe. Understanding the interplay between the Big Bang and inflation requires delving into these concepts with greater detail. The Big Bang is often thought of as the moment when time, space, and matter began. However, inflation suggests that this is not the full story. Inflation posits that the universe expanded exponentially before the Big Bang, smoothing out the initial conditions and setting the stage for the formation of galaxies, stars, and planets. This inflationary period also helps resolve major cosmological issues, such as the horizon problem, which questions how distant regions of the universe share the same temperature despite being causally disconnected since the Big Bang. Inflation explains that these regions were once closely connected before rapid expansion drove them apart. Similarly, the flatness problem, why the universe's geometry is so perfectly balanced, finds a solution in inflation, as the rapid growth would have stretched any initial curvature to near flatness. Yet, even as inflation addresses these challenges, it raises profound new ones. If inflation continues indefinitely in some regions, creating countless pocket universes, then our universe might be just one of many within a vast multiverse. This perspective not only changes how we view the Big Bang, but also complicates our understanding of the ultimate origins of existence. Inflation suggests a universe that is dynamic and eternal in some regions, while finite and bounded in others. Such ideas force us to grapple with the possibility that the observable universe is merely a small part of a much larger cosmic landscape. Exploring these questions demands not only scientific inquiry, but also philosophical reflection, as we attempt to understand the nature of reality and our place within it. Thus, inflation, dark energy, and quantum fields collectively form a complex narrative of the universe's origins and evolution. They challenge traditional notions of nothingness and beginnings, suggesting that even in the absence of matter and energy, the universe is far from empty. These concepts invite us to rethink our understanding of space, time, and existence itself, offering tantalizing glimpses into the profound mysteries of the cosmos.